this is a extra session for you to revise some of the important topics in our lectures. Uh, in this introduction section, we will be discussing about some of the important section that is uh, that you should be uh, revising for your final exams. Okay. So this is the course contents. So if you see uh, in our course, two of our early weeks courses were uh, introducing you with the methodology of CFD using two different simple problems. And in week 3, we have discussed about the governing equations of the fluid flow. Then week 4, we have discussed equation for incompressible flow and boundary conditions. Then how we can use finite different approximations to discretize the governing equation in CFD. Then some of the core concepts that is required for the schemes and the methods that we use in CFD were discussed in week 6. Then the solution, the methodology for solving Navier-Stokes equation for compressible flows in CFD were discussed in week 7. Then some advanced topic that is incompressible flows, how to use week 8 is on how to solve incompressible flows using the existing other solvers. These in the video itself, the faculty is giving a hint that these are advanced topics. So even if you are not able to pick these up, it's still okay. The idea of the course is for you to get uh, familiar with the methods and the basic structure of CFD uh, methodology and how it can be practiced. Then week 9 and 10 is on solution methods or iterative methods. Uh, both basic methods and advanced methods have been discussed here. Then how finite volume method. We have all this weeks we have been discussing with finite difference method. In week 11, we have seen how control volume uh, approach in a CFD, that is finite volume method. Also, other uh, grid generation techniques, how we can create meshes for our geometry, and what's the difference between a computational mesh and the geometrical mesh. And in week 12, it's about the turbulence modeling. So let's start our revision session. So first question, which of the following formulae is a good approximation for dou square u by dou y square at a grid point I comma j? So our options are option A, u at j minus 1 comma I minus 2 times u at j comma I plus u at j plus 1 comma I, the whole divided by delta y square. Option B, u at I comma j minus 1 minus 2 times u at I comma j plus u at I comma j plus 1, the whole divided by delta x square. Option C, u at I comma j minus 2 times u at I comma j plus 1 plus u at I comma j plus 2, the whole divided by delta y the whole square. And option D, none of the above. So the question is on how to discretize or how to approximate our partial differential equation to a linear equation. I can try to answer the question. Okay, so to answer the question, we need to know the Taylor series expansion. So we have already seen that the partial differential equation is mostly approximated using Taylor series equations. So a basic Taylor series equation for a variable x which is continuous and differentiable. That means my f of x should be continuous and differentiable. That is the two requirements to apply Taylor series. So for then with Taylor series, f of x can be written as in an expanded form of f of xi plus x minus xi into dou f by dou x at I plus x minus xi the whole square by 2 factorial into dou square f by dou x square at I plus etc. up to, this is the general term, x minus xi the whole raised to n by n factorial into dou raised to n times f by dou x raised to n at I plus higher order terms. H denotes higher order term. So if you are approximating, if you are considering f of I plus 1, that is, if x is at a point I plus 1, then the expansion becomes this f of I plus 1. Then we have to substitute all the points which had x with xi plus 1. Then f of xi plus 1 is equal to f of xi plus xi plus 1 minus xi into dou f by dou x at I plus xi plus 1 minus xi the whole square by 2 factorial into dou square f by dou x square at I plus higher order terms. Again, if we are moving backwards, that is, if we are moving a step behind I, it will be I minus 1. So for f of I minus 1, it will be f of x I minus 1. It can be, which can be written as f of xi plus xi minus 1, because we are substituting all the x's with xi minus 1. Xi minus 1 minus xi into dou f by dou x at I plus xi minus 1 minus xi the whole square by 2 factorial into dou square f by dou x square at I plus h. So if we are to take dou f by dou x, this term, out of this equation, that is, if we are writing equation A, then we are taking out dou f by dou x at I from equation A, then it will be f of I plus 1 minus f of I divided by x of I plus 1 minus x of I minus xi plus 1 minus xi by 2 into dou square of by dou x square plus higher order terms. So same thing we can get from this also, f of I minus 1. So if you are taking the second equation, then it will be looking like this. dou f by dou x at I is equal to f of I minus f of I minus 1 by delta x I minus 1. This delta x I minus 1 is x of what we have seen here, this term x of I minus 1 minus x of I. This will be the two equations from the forward differencing and backward differencing. Hence it is called forward difference scheme, and this is backward difference. If you are summing these two equations, if you are adding up these two equations, then this f of I term will be cancelled out. Also the xi terms will be cancelled out, and then the equation becomes something like this. That is dou f by dou x is equal to f of I plus 1 minus f of I minus 1 divided by x of I plus 1 minus x of I minus 1. So this is actually 2 times x of I plus 1 minus x, or x I minus 1 minus xi. So which can be written as 2 times delta x. So this is called central differencing scheme, CDS. Again, we have to find the second derivative. So to find dou square f by dou x square, then we can use these two equations. We can take dou f by dou x at I plus 1 minus dou f by dou x at I, the whole divided by xi plus 1 minus xi. Then again, if we are substituting the values for these from which we have already found out, then the equation and reducing equation becomes something like this. That is f of I plus 1 plus f of I minus 1 minus 2 times f of I by delta x square. So this is the approximation for dou square f by dou x square. So what we want to do is to find dou square u by dou y square at I comma j. So what we have is a two-dimensional coordinates. So here for x we only it was for x, so we only change the I values. Here we have to find for y, that is vertical direction. So we will be keeping the I values unchanged, only varying the j values. So our equation becomes u of u at I comma j plus 1 plus u at I comma j minus 1 minus 2 times u at I comma j. Let's read it as u of I comma j divided by delta y square, because we are moving in vertical direction. What we have to find is dou y square. So it will be delta y square. So such an option was not available in our list. So our answer is option D, that is none of them. Moving on to the next question. Consider steady developing laminar flow in a circular pipe. Which of the following statement is true for this flow? Options are statements are: first one, velocity profile changes axially. Option 2, velocity profile changes radially. Option 3, statement 3, pressure varies linearly in the axial direction. Fourth statement, pressure remains constant. So the options are combinations of these statements. Option A, statement 1 and 2. Option B, statement 2 and 4, option C, statement 2 and 3, option D, statement 1 only. You can try to answer the question. Okay, uh, the, here what you have to give your attention is to the question is about steady developing laminar flow. So steady times implies that dou by dou t of any times in our equation is 0. Developing means it is not fully developed, that the the boundary layer, the effects of boundary layers still exist. And laminar flow, which means it's not turbulent. So, this is a uh, flow inside a pipe. So you can see here the velocity. If you assume a uniform velocity coming inside, profile will be like or similar. Then when it hits the boundaries of the tube or the duct, circular duct, if the boundary layer starts to form and the boundary layer starts to reduce the velocity, and it changes its shape from rectangle shape to something like this one, and it will eventually keep on changing the profile uh, until it uh, becomes a parabolic profile. We know that is the parabolic profile is the velocity profile inside a circular duct. So the flow is governed by a Hagen-Poiseuille equation error. So our question was for developing region. So it was for our this region. The question for here you can see the velocity is varying in axial direction because the shape is something like here, and it is changed to this one. So we can say the velocity is changing axially. Also, you can see the radial variation. There is a velocity in the center is not in the going towards the peripheral, it is reducing. So in r direction also it is reducing. But linear pressure, linear fashion of pressure drop is only in fully developed region. So we cannot take it. And the other thing is pressure remains constant. From the from the graph of the pressure, we can see pressure is decreasing. So only statement 1 and 2 stands. So our answer is option A. Moving on to the next question. Consider one-dimensional flow governed by d square u by dy square is equal to constant over a height h. The interval h is divided into 30 equal segments. The upper wall moves to the right at a speed of 1 meter per second, while the lower wall is stationary. The number of discrete equations are. So the question is asking for the number of equations we have to discretize. Options are option A 29, option B 30, option C 31, option D 28. So in the question it is given that this interval h is divided into 30 equal segments. So from which we can deduce how many equations will be there. Try to answer the question. Okay, so it is for n segments. General rule is for if we are discreting into n segments, then there will be n plus 1 discretized points. So that is, this is a line, and we are discretizing it into four equal parts. So this is the initial point, first session, second, third is end point. So we can see there is four, four segments, but now there are five nodes: one, two, three, four, five. So for four sessions, we need 4 plus 1, that is 5 nodes. That's how it is. For n segments, there will be n plus 1 equation. So for in our question, it is 30 segments, then there will be 31 points. But it is given that uh, the upper wall moves at a speed of 1 meter per second, and lower wall is stationary. So the u is equal to 1 meter per second, the upper wall, and here u is equal to 0. So these two, when we have given the conditions here, then we don't have to discretize it because we don't need to find the values of u here. So we only need to find the rest of the uh, find u values for the rest of the points inside these upper and lower boundary. So total we have 31 points. Then two two boundaries we have applied boundary conditions. Then 31 minus 2, 29. So we have to find u values at 29 points. So at 29 points we have to discretize the equation dou square u by dou y square is equal to constant. That is our option A is the solution. Next question. The correct equation governing the fully developed flow in the x direction through a rectangular duct is. Our options are: option A, dou square u by dou x square plus dou square v by dou y square is equal to 1 by mu dp by dx. Option B, dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu dp by dx. Option C, dou square u by dou x square plus dou square u by dou y square is equal to 1 by mu dp by dx. Option D, dou square w by dou x square plus dou square w by dou y square is equal to minus 1 by mu into dp by dx. You can try to answer the question. So here the question is saying, see that here the equation is for fully developed, not for developing, and the flow is in x direction. So if the flow is in x direction, then our cross section will be on YZ plane. So that's with that hint you can try to answer the question. So we can consider the momentum equations in x direction. In x direction, it is our velocity component is u. Then considering uh, v and w components to be 0, these values become 0. Also for steady flow, dou by dou t becomes 0. While applying u and w is equal to 0, then this dou u by dou x term becomes also 0 because the flow is fully developed. So entire left hand side will be zeros. And also if we neglect the body force term, only terms existing will be minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. Again this term will be uh, 0 because dou u by dou x is not there, so this term won't be there. Then only existing terms will be this and this. So if we are rearranging it, our equation, our answer will be dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu into dp by dx. That is our second option, option B. Moving on to next question. Which discretization method is known for its strict conservation property, making it ideal for fluid flow problems? So the question is on conservation property of schemes. Which of the following discretization method follows a strict conservation property? Options are option A, finite difference method, option B, finite element method, option C, finite volume method, option D, all of them. You can try to answer the questions. Our answer is option C, finite volume method. Because in finite volume method, what we will be doing is we will be integrating, we will be considering control volumes. We will be discretizing. While discretizing, these cells will be considered as individual volumes or discrete cell volumes, where our governing equations will be integrated. So integral form of our governing equations guarantees the conservative properties. So when the uh, uh, equation guarantees conservativeness, so the it implies that the net outflow from one particular volume will be equal to the net inflow in the next volume. So there won't be any loss or there won't be any difference in the uh, cell interfaces or volume interfaces. Next question. What is the main advantage of forward and backward difference schemes compared to the central difference scheme? So we have seen in the first question, we have seen the three different schemes derived from Taylor's series expansion. That is forward difference, backward difference, and central difference scheme. So the question is about the advantage of forward and backward difference schemes over central difference scheme. Options are option A, higher accuracy for all derivative approximations. Option B, simpler implementation on non-uniform grids. Option C, better stability for certain types of equation. Option D, ability to handle complex boundary conditions. So our answer is option B, simple implementation of non-uniform grids. Because if you remember that uh, in forward and backward difference schemes, we only need information from one side. That is, in forward scheme, the difference is in I plus 1 and I, whereas in backward difference scheme, it is I and I minus 1. So in both these schemes, need information from either one of the either sides. So such such schemes will be easier to implement for non-uniform measures. While as in central difference equation, there won't be any I. The difference will be in between I plus 1 and I minus 1. So the particular value or particular property of the current cell where we are evaluating the particular property won't be reflected in our solution. Next question. What is the primary factor to consider when choosing a meshing strategy for a particular CFD problem? So this question is about uh, consideration on how to mesh. Options are cost of the meshing software. Option B, user experience with the meshing tool. Option C, balance between accuracy, computational cost, and meshing effort. Option D, availability of predefined mesh templates. You can try to answer the question. So, while going through our course, you would have understood that this uh, meshing software, cost of meshing software, and user experience with meshing tool is not uh, the primary objectives when we are uh, opting for a meshing strategy. So, why we mesh our domain? Because to get reasonably good solution for our CFD problem. So, our meshing strategy would be aimed at our requirement. That is, our requirement is reasonably good solutions. So, for that, option C, that is balance between accuracy, computational cost, and meshing effort. Thus, we should be balanced. We need good accuracy, but without increasing the computational cost and meshing effort beyond uh, beyond some considerable level. So option C is our answer. Next question. Which of the following factors primarily influences the accuracy of a CFD simulation result? Option A, geometry complexity. Option B, mesh type. Option C, mesh density. Option D, software used for meshing. So the question is on the primary factors that can affect the accuracies of CFD simulation result from the given list. You can try to answer the question. So our answer is option C, that is mesh density. Because in mesh density is the level of refinement. So the mesh should be sufficiently refined, that is the uh, geometric proportions of the cells should be small enough to capture the uh, flow changes, the parameter changes uh, uh, for the for the CFD problem which we are analyzing. We uh, aimed at finding some of the flow properties. Then the mesh should be reasonably fine enough, reasonably fine. That is, geometric proportion should be small enough to capture the small, even the small variations. The how much small will be depending on our requirement, but it should be give the uh, reasonable accuracy that we are expecting. That is a level of mesh refinement. And another name for mesh refinement is mesh density. That is, like the normal density, you can think of how much cells are there in a some unit volume of our domain. So mesh density is which directly impacts the accuracy of the solution. Moving to next question. When comparing a structured and unstructured mesh with the same number of elements for a simple geometry, which one is likely to have better solution accuracy? Options are option A, structured mesh, option B, unstructured mesh, option C, both will have the same accuracy, option D, depends on the specific flow problem. You can try to answer the question. So option A, that is structured mesh, will give better solution accuracy when it, both of them have same number of elements, because the structured element, uh, even with the simplest example you can understand. So This is the two structured elements, and this is unstructured element, triangular. So even by computing the inter centroidal distance, this in structured mesh uh, it will be easier compared to finding here, because here it will be more inclined, and also finding the geometric proportions of the intercentral length, uh, the base length, all such things will be difficult in unstructured mesh, whereas in structured mesh uh, all such calculations will be easy, because in structured mesh it will be somewhat correlated to our coordinate axis. So next question: how are boundary conditions implemented in CFD methods? The questions on boundary conditions. Options are: option A, they are applied directly at the grid points in FDM or element nodes at FEM, that is finite element method. Option B, source terms are incorporated into discretized equations. Option C, both A and B are used depending on the specific boundary condition. Option D, it depends on the specific solver algorithm used. You can try to answer the question. So we know what is boundary conditions. So here option A and option B are true. So answer will be option C. That is both option A and B, depending on the specific requirement of the problem or the consent problem at your hand. So option C is our answer. Option A is explaining about the direct application of boundary condition, which is called digital boundary conditions, while the option B is saying about Newman boundary conditions, or something in terms of source terms. Next question: which of these best define the Dirichlet boundary conditions for the property phi at the point B in the boundary? Option A, dou cube phi by dou x cube. Option B, dou square phi by dou x square. Option C, dou phi by dou x. Option D, phi at B. That answers the question. So even from the previous question, we can see that when boundary condition is directly applied, it is Dirichlet boundary condition. So here it's a Dirichlet boundary condition. So the uh, boundary condition should be directly applied without any conversion. So if our property is phi at B, then answer will be option D, that is phi at B. So we don't have to differentiate phi. So we can directly apply phi to B. That's what the residual boundary condition says. Next question: which type of mesh is best suited for complex geometries with curved surfaces? So the question is about which type of mesh should be preferred for complex geometries with curved surfaces. Option A, structured mesh. Option B, unstructured mesh. Option C, hybrid mesh. Option D, all of the above. You can try to answer the question. So to answer the question, we should understand the different types of meshes. And obviously, our answer is option B, unstructured mesh. So here, the question asks for complex geometry and that too with curved surfaces. So, uh, uh, first kind of mesh in our option was structured mesh. So in structured mesh, this is an example for structured mesh. So if you can see, it is kind of a rectangular grid. Even though the sizes of rectangular elements, the rectangular cells varies from bottom to bottom vertically. It is almost the shape is rectangular everywhere. So it's not vary. So such kind of mesh is called structured mesh. So this in Cartesian mesh is a structured mesh where uh, our grid lines will be always parallel to the Cartesian coordinate axis. So that's a Cartesian mesh. So this next one is also structured kind of mesh, but it is somewhat curvilinear mesh. So even though it is not keeping the rectangle shape always, but it is almost conformal to the uh, axis regarding axis. So even if it is not uh, following the Cartesian coordinates, if it is will be following cylindrical axis or spherical axis or some coordinate system. So when it's an unstructured mesh, you can see these are the examples for unstructured meshes. So the unstructured meshes is completely random. It will try to uh, subdivide the given volume or area uh, into uh, smaller domains of required refinement with uh, any type of elements. Here, if you see, here's a lot of quadrilateral elements is here, where here it is triangular or tetrahedral elements are used, and here it is polygonal elements. So you can see almost all uh, elements differ from each other in this type of mesh. So you can see here in the example itself, it is showing curved surfaces. So in curved surfaces, mostly uh, or easily meshed with unstructured mesh. Next one is hybrid mesh. So hybrid mesh is a combination of structured plus unstructured. So if you see here, uh, this was one geometry, but this much portion is uh, meshed with structured mesh, but the top portion is with meshed with unstructured mesh. So we can choose different type of meshing for different regions of the same computational domain, depending on our accuracy or computational needs. So this is a rect rectangle and sorry, the hexagonal and tetrahedral combination. So here, if you see, this is a hybrid tetrahedral. You can see the domain. This is a aerofoil or uh, airplane wing. The surrounding areas is meshed with uh, tetrahedral mesh, but when it is coming near to the wing or the surface, we have used uh, rectangle or hexagonal meshes so that we can capture the boundary phenomena easily. So here the same is done, but instead of tetrahedral, we have used polyhedral mesh. So here also, if you can see, the far domains are meshed with polyhedral, where these are with structured mesh. Moving on to next question. What is the key difference? What is the key difference between explicit and implicit boundary conditions in CFD simulations? So, key difference meaning important difference between explicit and implicit boundary conditions. Option A, explicit conditions specify values directly at the boundary. Option B, implicit conditions involve solving additional equations at the boundary. Option C, explicit conditions are more accurate while implicit are faster. Option D, explicit conditions require special meshing near boundary. You can try to answer the question. The key difference is that in explicit boundary condition, as the name says, explicit means clearly said, explicitly defined or something. So, in explicit boundary condition, as the name suggests, the uh, value of the variable is directly set at the boundaries. So, this is much simpler method of boundary condition, and that is the key difference between implicit and explicit method. Whereas in implicit boundary conditions, we need to uh, model some partial differential equations or governing equations at the boundary, and then we have to discretize the same. So first we have to, in implicit, we have to convert the physical boundary condition to partial differential equation, then we will have to discretize it. Next question, you are simulating laminar flow through a pipe using finite difference method. The discretization scheme is known to be consistent, but the initial condition for the velocity field is not smooth. What can you expect about the solution? So the question is about, while simulating a laminar flow through a pipe with finite difference, what will happen if the velocity field is not smooth? Option A, solution will converge to the exact solution as grid size is refined. Option B, solution will exhibit numerical oscillations even after grid refinement. Option C, solution will be accurate but only for a limited time. Option D, the solution will not exist at all. You can try to answer the question. Our answer is option B. That is, the solution will, we can expect solution to exhibit some numerical oscillations even after the grid is refined, because when the initial conditions are not smooth, so even after the grid refinement there will be some fluctuations in the solution even after the grid refinement. Next question, in the energy balance equation, what does the convective term represent? Option A, rate of heat generation due to internal sources within the control volume. Option B, rate of heat transfer due to temperature gradients within the fluid. Option C, rate of heat transfer due to thermal conductivity across boundaries. Option D, rate of work done by the fluid on its surroundings. So the question is about convective time of the energy balance equation. You can try to answer the question. Our answer is option B. That is, rate of heat transfer. Uh, Rate of heat transfer due to the temperature gains within the fluid. That's convection, as convection is a fluid property, are mostly related to fluids. So, how the heat is being transported by the fluid. That is what is expressed by convective types. So option B is our answer. Next question. What physical property mainly influences the thermal conductivity in the energy balance equation? So question is about the physical property influencing thermal conductivity. Option A, fluid viscosity. Option B, fluid density. Option C, fluid specific heat capacity. Option D, fluid thermal diffusivity. You can try to answer the question. So if you check the uh, energy balance equation, our RHS will be having thermal diffusivity instead of rho. So that is thermal diffusivity alpha is equal to K by rho Cp. So where K is the conductivity, rho is the density, Cp is the specific heat. So all the other three is being uh, accounted. Apart from viscosity, this density, uh, conductivity, as well as specific heat, all the three properties have been uh, comprehensively included in the thermal diffusivity. So our answer is option D, thermal diffusivity. Next question, which property is not essential for a CFD problem to be well posed? The next question is on well posedness of a CFD problem. Options are existence of a unique solution. Option B, continuous dependence of the solution on its initial and boundary conditions. Option C, finite solution at all points of the domain. Option D, compatibility of the governing equation with the boundary conditions. So well posedness is the property of the CFD problem to have a existence of a unique solution, and the solution should be changed with when there is a change in the initial or boundary conditions. So option is option C, finite solution at all points of the domain. Because finite solution at all points of the domain is something related to boundedness of the boundedness property, and it is not strictly needed for well posedness. Next question. In a CFD simulation of incompressible flow, which of the following is not a crucial aspect of ensuring well posedness? The next question is also on well-posedness? Options are: option A, satisfying the continuity equation; option B, imposing appropriate pressure boundary conditions; option C, using a conservative discretization scheme; option D, employing time stepping scheme with CFL stability criteria. You can try to answer the question. The question is about which is not a crucial aspect of well-posedness. Option D is our answer, because option D is not directly related with our well-posedness, because CFL criteria is current Friedrich list criteria, where uh, it is it uh, gives the bare minimum requirement stability of a scheme. So for in CFL stability criteria, what we have to think is how the scheme will be stable uh, for a given problem, and uh, that is not directly related with the well-posedness, while other things that satisfying the continuity equation and also obeying the boundary condition, conservative property, all the three are related with well-posedness. Next question is, what is the difference between well-posedness and ill-conditionedness? Conditionedness. Options are: well-posedness refers to the existence of a solution, while ill-conditionedness refers to the difficulty of obtaining it numerically. Option B, there is no difference, there are same concepts. Option C, ill-posedness is more severe condition than well-posedness. Option D, well-posedness only applies to steady-state problems, while ill-conditionedness applies to transient problems. You can try to answer the question. So our answer is option A. Well-posedness refers to the existence of solution, while ill-conditionedness refers to the difficulty in attaining it. Well, as we discussed, well-posedness only says that the system should be solvable. It should have a unique solution, and it should well-posedness is solvable unique solution, it should reflect boundary conditions and initial value. So while ill conditionedness says that the difficulty in attaining it, because there is something called condition number. That is when we uh, discretize the governing equations. The governing equations are discretized algebraic equations. This can be written in the form Ax is equal to T, where A is the coefficient matrix of our unknowns. So for this uh, coefficient matrix, the lambda max, that is eigenvalue, maximum eigenvalue divided by minimum eigenvalue, is something called a condition number. If the condition number becomes too large, then the solvability of the system becomes difficult. So even small uh, errors creeping into the elements of this coefficient matrix can affect the condition number, which will in turn makes it difficult to solve. Next question. Consider a CFD simulation with moving boundary. How does the movement affect the well posedness of the problem? Option A, it has no impact as long as the governing equations remain the same. Option B, it can introduce additional challenges in specifying well posed boundary conditions. Option C, moving boundaries are always make the problems ill posed. Option D, moving boundaries only affect the accuracy of the solution, not the well posedness. You can try to answer the question. So, CFD simulation with moving boundaries will make the boundary conditions more difficult. So thereby we have to properly model, because we have to specify the boundary conditions so well that it should reflect in the system without affecting its solvability. So one condition in well posedness is that it should reflect all the small changes in the boundary conditions. So when the boundary is moving, that moving boundary condition should be or the variation of flow property due to the moving boundary should be reflected in the well posedness. For that, we have to model the moving boundary conditions precisely to get a unique solution. Next question. What is the main advantage of using higher order differencing scheme compared to a lower order differencing scheme? Options are: Option A, reduced computational cost. Option B, improved stability. Option C, increased accuracy with fewer grid points. Option D, easier implementation in complex geometries. You can try to answer the question. So we have seen what is higher order differencing and lower order differencing. When we are using the Taylor series expansion, so for dou u by dou x, there will be some equation plus some higher order terms. These higher order terms will be in terms of delta x or delta x square or something. So uh, when we are going for higher order differencing schemes, then the truncated values, truncated errors that the higher order terms that we are getting truncated from the approximation will be smaller. The magnitude of the truncated truncated part of the Taylor series expansion will be lower. So such schemes are called higher order schemes. When if the order of terms getting truncated is lesser, that is, then the truncation value will be higher, which will reduce the accuracy. So the higher order differencing and lower order differencing gives different accuracies. Higher order gives higher accuracies. So option C is our answer. Increased accuracy with fewer grid points. Next question. When discretizing the diffusion term in Navier-Stokes equation, which scheme is generally preferred? So the question is, when discretizing the diffusion term, which scheme is preferred? Option A, upwind differencing. Option B, central differencing. Option C, downwind differencing. Option D, any of the above depending on the flow conditions. Our answer is option B, central differencing equation. Sorry, central differencing scheme. So in diffusion terms, so diffusion terms is uh, the spreading of flow property due to the density difference. So these diffusion terms uh, are mostly discretized with central differencing schemes. Next question. The CFL condition, that is current Friedrich-Lewy condition, is the stability criterion used in explicit time marching schemes. What does the CFL number represents? So mostly, not mostly, the CFL levy condition is imposed by uh, giving some condition called CFL number. So what is this CFL number represent? That is our question. Option A, the ratio of viscous to diffusive forces. Option B, ratio of time step to characteristic wave speed. Option C, the order of accuracy of spatial discretization scheme. Option D, convergence rate of iterative solution process. So our answer is option B, uh, the ratio of time step to characteristic wave speed. Actually, it's not the ratio of, it's not a ratio, but the relations between characteristic wave speed and time step. That is, CFL number is C delta t by delta x, where C is our characteristic wave speed, delta t is our time step, delta x is our spatial discretization. So the main idea is that uh, uh, our cell uh, length and uh, time delta t, if that we know speed is uh, delta x by delta t, or that is a length by time. So this ratio should be uh, uh, less small enough to capture the data being, or sorry, the property being transported. So when a transport the property phi is being transported, then it will suppose it is transported in with the wave speed characteristic wave speed c, then our dimensions of the spatial discretization delta x and temporal discretization delta t should be small enough to capture the variation in this transporter property. Next question. Lack's theorem states that option A, convergence is assured for well-posed linear initial value problems. Option B, stability is assured for well-posed linear initial value problems. Option C, consistency and stability are sufficient for convergence for the well-posed linear initial value problems. Option D, none of the above. answer is option C. That is, Lack's theorem states about the well-posedness criteria for linear visual value problems and states that consistency and stability are sufficient for the convergence of linear initial value problems, that is, linear IVPs. Next question, which of the following does not affect the stability of a hyperbolic problem? Uh, Properties are mesh spacing, velocity, viscosity, and linear boundary value time step. Options are A only, sorry, option A, mesh spacing only, option B, velocity and viscosity, option C, mesh spacing and velocity, option D, viscosity only. You can try to answer the question. Our answer is option D, that is, viscosity mostly depends on uh, uh, mostly not dependent on the viscosity. The stabilities, we have already seen that uh, for CFL criteria, CFL number is C delta T by delta X. So here it is delta X is there, delta T is there, velocity is also there. So all the three is uh, dependent, is required for calculating the stability criterion itself. But the third one, that is viscosity, is not required to predict the stability. So our answer is viscosity only, that is 3 only. Next question. If wiggles appear in a numerical solution, then what can be done to eliminate them? Decrease the time step, decrease grid spacing, use more accurate scheme. Option A, 1 only. Option B, 3 only. Option C, 2 only. Option D, both 2 and 3. Wiggles, that is the fluctuations in the results, or uh, oscillations in the numerical solutions are appearing, then we should decrease the grid spacing to eliminate them or to reduce them. That is our option is answer is option C. Next question is on the properties of schemes. Accuracy refers to statements are: first one, how fast the scheme converges to the exact solution. Second statement, difference between numerical solution and the exact solution. Option C. Sorry. Third statement, scheme's ability to preserve physical properties. Of, fourth statement, how sensitive the scheme is to small changes in initial conditions. Fifth statement, the scheme's ability to find exact solution. Options are statement 1 and 2. Option B, statements 1, 2 and 3. Option C, statements 4 and 5. Option B, all of the above. Option C is our answer. That is, accuracy refers to how sensitive the scheme is to small changes in the initial conditions and the scheme's ability to find the exact solution. Next question is on conservative property. A scheme is conservative if it, options are, always converges to a solution regardless of initial conditions. Option B, preserve some physical quantity like mass energy over time. Option C, guarantees a solution within a specific bound. Option D, minimize the error between the steps. Our answer is option B, that is preserve some physical quantity over time. So we have already discussed why finite volume scheme, uh, why finite volume method is conservative, because it conserves the fluid property or the property being transported. So the same is here. The conservative property defines the conservation or preservation of some physical quantity. Next question. Boundedness ensures which of the following? Options are, the numerical solution remains within a finite limit. Option B, the scheme always produces a unique solution. Option C, the error between numerical and exact solution decreases with time. Option D, the scheme can handle large initial conditions. Yes, as the name suggests, boundedness. the numerical solution should remain within a finite limit. So it should be bounded. So for example, if we have three different cells, this is P, this is west, and this is east, then uh, the value at phi of P should be in between phi of W and phi of E. So that is, it should be bounded by the upper limit or lower limit, whether phi phi at W or phi at E is greater will depend on the problem. But the thing is, while discretizing, it should be bounded by these values. So it should not go uh, beyond phi W or phi E. It should be in between phi W and phi E. That's what called boundedness. Again, the question is on boundedness. A scheme is bounded if the solution values, option A, remain too close to the initial condition, option B, never become negative or positive for initial values, option C, approach a constant value as time increases, option D, can be arbitrarily large depending on the scheme. Yes, our answer is option B. That's again, as I said earlier, is 5P, 5E, and 5W. That if suppose this is a lower value and this is a higher value, then it should not, the value of 5P should not be become negative for this lesser value, or it should not uh, increase beyond this H value. That it should not be become, and the 5P, if it was positive at the beginning, the initial value, it should not become negative while we are solving the system. While iterative process, the 5P should not become negative. Next question is on the consistency of the scheme. A scheme is consistent if, options are, it becomes exact as the discretization approaches zero, B, the error remains constant for all time steps, option D, it approaches a smooth continuous solution, option D, it is computationally efficient for large problems. Our answer is option A. That is, it should become exit approach the exact. Uh, it should become exact as the discretization approaches zeros. That is, uh, partial differential equation is converted into algebraic equation using some scheme. Then when this discretization, this discretization delta x or delta y, when it approaches zero, the algebraic equation should approach the partial differential equation, or the solution of the algebraic equation should agree with the solution of partial differential equation. That is called a consistency. Next question is on convergence. Which of the following statement about convergence is false? Option A convergent scheme approaches exact solution as discretization size tends to zero. Option B, convergence guarantees the scheme will always produce a solution. Option C, a stable scheme is necessary condition for convergence but not sufficient. Option D, non-convergent schemes can still be useful for qualitative analysis. Option B is our answer. This is a false statement. Next question. An unconditionally stable scheme for an explicit ODE, that is ordinary differential equation solver, guarantees which of the following? Option A, the solution will always converge to the exact solution. Option B, the scheme is always accurate regardless of the time step. Option C, the solution will not grow unbounded regardless of the time step. Option D, the scheme is computationally efficient for all problems. The question is on stability of the explicit ODE solvers. Our answer is option C, that a stable scheme will not allow the errors to grow unbounded. So our answer is option C.